How's everyone this morning? Yay, thumbs up. Like it.
Good. How are you doing?
Good, good. Been renovating all weekend, so I feel like I achieved things.
Sounds productive. Cannot
Yeah,
relate.
right. 9:30 Monday morning. That means journal club time, Neuroccino time. And today we have Chris, who's going to present on the exciting topic of statistical power in network neuroscience. Chris, if you can share the link, thank you, and take it away.
All right, so yeah, I found this paper about the controversial topic of statistical power in network neuroscience. It's been discussed quite a bit in the well, since fMRI basically, but it's not only about fMRI, it's also about any kind of connectivity studies. So also structural connectivity. And basically they discuss how we estimate the statistical power of studies and some of the hidden uh, like some of the things that we don't often consider when we calculate the statistical power that we have in a study, and how we could improve it in the field. It is a review paper, but they also give some ideas to help with the problem. Um, I will start with, so they made really cool figures um and boxes that illustrate what's happening. So they explain a bit about the statistical power. So we often hear about the type 1 and type 2 errors. So the type 1, the problem of the false positives is what we try to avoid when we use a threshold, when we use like a t-test or something, a threshold of the p-values. So when we say we have a threshold of 0.05 or of 5%, that means that 5% of the tests that we are doing are potentially false positives. So that's illustrated with the first part of the figure. So you see one part of the test can be false positives, but there is another. So that's a very discussed type of errors. It is also corrected. So when we do multiple tests, we have a multiple comparisons corrections and stuff like that. But another type of error that is very relevant for the connectivity studies in the brain is the type 2 errors where we have false negatives. So we are not capturing all the all the relationships in our data because, for example, we are overcorrecting. So that's illustrated by the second part. So uh, the power. So if we set our threshold of significant values too harshly, we get a statistical power that is very limited for our data. Um, and they explain that it's a problem in a lot of studies in connectivity. Um, yes. So they approach the connectivity analysis, the connectivity studies with the graph theory. So even though not all the connectivity studies are using graph theory directly, The moment you have a connectivity matrix, that's basically a graph. So you can also interpret most of the connectivity studies as a graph theory problem. And it's just easier to explain what basically you can put all the most of the studies in the under the same umbrella of graph theory, and you can see the some of the problems that you have in these studies. So a lot of the most recent studies are using network-based inference, but there are still a lot of studies that are using the classic we do a t-test between the different between the connectivity of the different participants, for example. But you have more and more studies that are looking at the clustering of the networks, the global efficiency, modularity, all these measures that describe the patterns of connectivity between regions in the brain. Yes, and the statistical power. So I think there is in the box. So yeah, I'll come back to the first. So basically, the statistical power that we have in a study is the ratio between the false negatives and the true negatives. And they explain that as a convention, as a standard, we have a strong statistical power when we have a ratio of 80% of true positives for 20% of false positives. So that's a little bit what studies should aim for. It's, of course, it's a threshold, so it's always a little bit arbitrary, but that they show in their review that not many studies are reaching these values. If I find the yes, so here they explain what they reviewed. They reviewed 1,300 connectivity studies, 300 DWI structural connectivity, and 1,000 fMRI studies between 2019 and 2022. And so you can see that there are not. So of course, having getting data for these kind of studies is always challenging because the acquisitions can be lengthy. So the number of participants is not very big. So of course that affects the statistical power. That's the first thing that we look at usually in studies. How many participants do we have? That gives us an idea of a rough idea of the statistical power that we could have. And just based on the sample size, they calculated the statistical power that these studies have. And you can see that for the classic, so they explained they classified the studies in 3 different types. So the classic t-test, where you compare just a single graph metric. Then similarly, you compare between the participants, but with multiple metrics. Here they took 5, 10, and 50. And finally, the more recent network-based statistics. And they calculated for the studies that used the different types, these different types of analysis, what was their statistical power. And the median for the first type, the just simple t-test on one metric, you can see that just a little bit more than 10% of the studies had the statistical power, a strong statistical power according to the 80% threshold, with a median at 47%. But then for the other types of analysis, you can see that the statistical power of the studies is going down very quickly, depending on the number of metrics that are compared. Because of course, when you use multiple metrics, you have to correct for multiple comparisons. And the classical way is to use the Bonferroni correction, which is good to avoid false positives, but it's also very strict. So it's increasing a lot the number of false negatives. So that's why you have a massive drop of the statistical power. And for the network-based statistics, it's not much better. You can see that's for the NBS. So that's 31%. The median of statistical power is 31%, which is quite far from the 80% that we would like. And also the thing is, only 5% of the 1,300 studies conducted a power analysis. So they explain that some of the studies, a large percentage are talking about the statistical power, but a very small percentage actually conducted a thorough power analysis before they did the study, which might be one part of the problem, of course. Yeah, so far, that's mostly about the sample size. So how much the sample size give us information about the statistical power. But what's interesting in this paper is that they don't only talk about the sample size. They explain that there are other aspects, other factors that affect the statistical power of analysis. So first, the effect size, that is actually but it's not studied as much, it's not discussed as much as the sample size. Sample size is the most straightforward. But the effect size is also very important because sometimes the variations that we have in the data is very small compared to the whole, so the variations for for significant effects that we are looking for might be very small compared to the whole variations of the data set, which also potentially decreases the effect size. But also you can have measurement errors, and I think we know in neuroimaging that can be a big problem. There are different types of measurement errors depending on the modality, depending on the task, depending on the type of analysis also that we do. And also they talk about the network, the nature of the networks that can also affect the effect size, the power, the statistical power. So first they talk about the reconstruction. So essentially, in the majority of the cases, the problem during the reconstruction of the network, based on our data. So we have the imaging of the brain, we have the imaging of the neuron, and we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. And then we have the imaging of the neuron. but then we have to decide what type of we have to decide of a network that will represent the different regions of the brain that we are looking at. And often, especially in fMRI, we use a threshold. And the threshold can greatly affect the statistical power because it's going to remove some of the connections that might actually be relevant or not, and also mix up real connections with connections that we that don't exist. Because if you remove a connection because of your threshold, that doesn't mean that the connection doesn't exist. That might mean that it's just weak compared to other connections. For example, in structural connectivity, when there is a connection, it's hard to say that if the measure is weak, that doesn't mean that there is no connection. That just means that the connection is weak. But if we remove it with the thresholding, we are actually saying now that this is not a connection, which is not what the data actually say, but that will increase the statistical power if we just look at the effect size and the sample size, because we reduce the number of comparisons. But that actually reduces the statistical power in the sense that we are missing some we are potentially missing some actual effects. And then there is the resolution. The resolution is, for example, when we choose an atlas to determine which are the regions that are part of the network. So this can also be kind of arbitrary because the size of the regions might be different. So we can have an atlas of a few regions, or an atlas with 200 regions that will completely change your statistical power, of course. Then you have the level of the analysis that you do, or the metrics that you're using. You can use more local metrics. So like the modularity of the nodes, for example, how they are connected to each other. But you could use other more global network metrics that will also change your statistical power. And finally, one interesting thing is that, especially for network-based statistics, they talk about the topology of the network that can actually quite a bit affect the statistical power. So I think they have a little bit more details. So sample size, effect size. Um, Yes. So here you have the degree of clustering. So it's like simulated networks, but and of course this is the snake-like network is a very extreme case, which is quite unlikely in the brain. But it's just to describe the different configurations of network that you can have that can affect your statistical power. And you see that the power is enormously reduced when you have some kind of sequential network compared to a more clustered and even like more loop looking network. And this is because the network statistics, the network-based statistics, are affected by the cluster, the degree of clustering of the networks. So these all these additional factors can modulate your statistical power. Do they have another box? Yes. So basically their advice is that we need to take those into account. And what is interesting, I find, is that they give a little idea, a little cheat sheet to calculate the statistical power of your studies and estimate these different factors. They give several different steps to estimate the different factors that can affect the statistical power. One thing that they also explain is the idea of differential power. Basically, they explain that these additional factors, they might be different across the brain. So you might have different measurement errors in different parts of the brain. You can also have thresholding that will affect differently different parts of the brain, because if you could think if a connection if connections are just inherently weaker in one part of the brain, that doesn't mean that weaker when we capture them with our method, with our functional imaging or our structural imaging. If they are weaker, it might not be because they are weaker actually in the brain, but it might be just because of our method. For example, with the structural connectivity, if there are crossings, if there are a lot of crossings, that will trouble the algorithm to reconstruct the connections. So it might create artificially weaker connections, which might actually be pretty strong in the real brain. So when we look at these data, when we do the statistics on this data, the statistics are going to take it into account as a weak connection, which might not actually be true. So if we have a measure of uncertainty for the our measures of connectivity, it might change across the brain. So they explain that it should be taken into account in the same way as the network topology might change across the brain. We might have a stronger clustering in one part of the brain and a weaker one in another part of the brain, which will bias the statistics that we will do in these different parts because of the statistical methods that we use. And that's why they advise so starting with the effect size, calculating a significant level. Optionally assess the reliability. And then at the end, they explain that you could have a power mask that would give a statistical power per edge for each edge in the network, instead of having a global statistical power for the study. They explain that it might be better to have local evaluations of statistical power so one thing, one maybe limitation to the study that I would say is that they say that you could mask it and just you calculate your statistical power and you say, oh, this region has a really low statistical power, so we remove it. I think that's a little bit too fMRI style. So I think it should be added as a covariate weighted in the statistics. But I guess that would be better to have a more accurate calculation of statistical power instead of having it for the whole study. So yeah, that was a pretty chunky paper, but that's basically it. There's a lot more details in the paper, but yeah, I'll stop here.
Thank you, Chris. Great paper. I love that there's a cheat sheet. That's what we need.
Yeah, yeah.
First hands up, Eva.
Hi, great talk. And it's actually so relevant to what I'm doing right now. This whole discussion about network analysis, and there's some great points raised. I'm just wondering, so the sample size you described. So if I do t-test, is the sample size, because if your groups are unequal, how do you deal with that? Like, for example, if one group I have a lot of people and another group I only had a few, because I was dealing with this and I noticed that if I look at the sample size that's very small, I get nothing. And then if I look, because in my sample, I was using MBS, but I had 3 groups. So I kind of looked at like 3 t-tests. I did another one and I did 3 t-tests, and groups that were actually like having very little people had nothing. And I'm like, is it actually real result, or is it just the result of underpowered sample? So how do you deal with unequal groups, and do you have any thoughts about that?
Well, statistics is not my forte, but I guess if you calculate the statistical power before you do it, you might have an idea of what's happening. Because, for example, for your small sample size, if you calculate your statistical power, you might see that your statistical power is lower than your variations in your analysis. So in your data. So you would see that your statistical power is not big enough to do any statistics on this group, for example. And then maybe find another method, or change the granularity. Maybe you would have an effect with a different granularity of your network. But at least, yeah, you would probably have a better idea if you calculate the statistical power of your statistics before. But then yeah, I'm not an expert in statistics, so I don't want to give you bad advice. But I think the
I was
statistical
just
power,
wondering,
yeah.
maybe, I mean, let's say if I will be determined to still do network analysis, does it mean that I can be a little bit less conservative my threshold if I have like, or is it other way around? Like, correct me if I'm wrong, because if it's too conservative, and yeah, I don't really
That's
know
always
how
a
to like deal in that
trade-off.
situation.
So, for example, if you're correcting with Bonferroni, you will be pretty strict on the false positives, because of course you don't want false positives, but you will also completely destroy your statistical power, and you will greatly increase the number of false negatives. So you need to find a good balance between the two. So depending on the number of comparisons that you have, you could use, for example, FDR. That could be less stringent, but also potentially increase the number of false positives. And in the network-based, I guess it depends on the method that you're using. But you might be looking also at the clustering, maybe also your thresholding that might be a little too stringent. The atlas, so the regions that you're defining, they might be too big or too small. And yeah, you could get more a better idea of your statistical power if you calculate it before, and see if you change the parameters, if you have a potentially a better statistical power without increasing the type 1 and type 2 errors.
It's just last very quick question about network topology as well, because you mentioned that if the network like goes like this, it's less likely for it to be detected, for example, network-based statistic.
Yeah.
And it made me think, like, in terms of like corpus callosum connections, does it mean that it's less likely to detect them as well?
So if you have less cluster, so the network-based statistics seem to be drawn towards the more clustered parts of the network. So you will have a stronger statistical power in more clustered area, but that's a virtual statistical power. So that can be an overestimation of the statistics in more clustered areas compared to less clustered areas. So if the topology of your network is very different from, it's not completely, it's not fully connected, for example, you might have a bias in your statistical analysis. So you might look at that as well. Yeah.
Thank you so much. Thank you.
Next question, I think Muge was first.
Yeah. Thanks, Chris, for this very useful and relevant paper. I think my question was also relevant, like connected to Yeva's question about this bias issue. So in this figure where you showed that the power of the analysis increases with high clustering, but yeah, I just wondering, like, is there because there should be some kind of like an overfitting issue there, like if you use the completely different sample, you might not be getting the same results, right? If you have such is there a way to, I don't know, go around that bias issue? Like I'm not familiar with network-based statistics,
so yeah, they give some guidelines, but at the same time, I kind of feel that they just say you might need to look at your parameters. It might not be optimal, but it feels that some of the statistics should be changed. So some of the methods that we're using to do the stats might need to integrate these biases because there's there's not much you can do if the statistical method is biased towards one part of the network. If there is nothing to change it, you can't just artificially say that this other part of the network, I mean, you could potentially, I don't know, increase the weight of your connections in the less clustered parts, but how do you determine what is a good weight to add? You would need to quantify the bias of the statistics to then counterbalance it in the rest of the network. So yeah, I don't think they provide a straight solution to that. But at least being aware that there can be a bias is a first step. And hopefully this would spark more discussions and potentially changes and development of better stats.
Okay, thank you.
So when you say we need to incorporate these biases in our analysis a bit better, how bad is it at the moment?
Well, when they talk about the statistical power in the studies that they reviewed, it is so I think they say that the false positives problem is the most studied type of errors. So at least we shouldn't have too many false positives. But there is still, I mean, we see that the reproducibility of some connectivity studies is quite difficult. So there should be still some false positives that are going around, but it could also be due to the very large amount of false negatives that they show here with the 1,300 studies, where you have less than 50% of the studies that have a strong statistical power. So that means that the majority they are missing the majority of the significant effects. So this is pretty bad. That could explain the low reproducibility as well, because if one study is getting part of the statistical effect of the significant effect, and the other study is getting the other part, they will say that they are in the disagreement. They disagree, but maybe it's just that they are capturing two different parts of one effect.
Okay.
So yeah.
Final question, Lilith.
Yeah, a quick question. Thank you, Chris, for this paper. Do they discuss also about Bayesian statistics as the
I thought about it when I
as
was
the
reading the paper, and they
alternative?
don't.
Like at all? There is no word
No,
about
no.
why?
There's no mention. Yeah, so I was thinking about it. I was like,
Just a little
that
paragraph,
looks like
no?
something that would be
Yeah.
really good with Bayesian statistics. It feels like that would help a lot. But no, they don't mention it. So I don't know if none of the studies that they selected have Bayesian statistics. That could also be because they don't understand Bayesian statistics very well, so they didn't talk about something they don't master. But yeah, I feel that Bayesian statistics might be a good way to help
Yeah,
with
but
this
I
problem.
think also, well, I don't think Bayesian statistics also will be the perfect solution. In Bayesian, they have own problems.
Yeah.
So this paper is also nice that it's trying to fix their own problems
Yeah.
within their paradigm. But yeah, I thought that at least some sentence, I don't know. But yeah.
I'm guessing that the being more aware of the statistical power would also help with the Bayesian statistics, right?
Mm-hmm. Yeah.
So yeah, I mean, it's good to be aware that there is a problem, because it's easy to just reproduce a method that has been used without really questioning if whether it's the right way to do it. So people need to be aware that there are potential problems.
Yeah. Cool. Thank you.
And really good advice in life as well. Go and fix your own problems.
Yeah.
Right. Thanks. That's all the time we have. Thanks for presenting that paper. Thanks for engaging in the Q&A. And I see you next Monday morning. Have an exciting week in science. Bye.
Yeah.
Bye bye.